food delivery app's proximity service crashed every 15 minutes with 500 errors. The container had 4 GB of RAM and was OOM-Killed. The team assumed a memory leak in the Geohash library, but the real culprit. The Quadtree stored every POI's full address and metadata, 2 million objects at 2 KB each, consuming 4 GB. During peak traffic, tree rebalancing doubled memory usage, triggering the OOM killer. Let's break down why this happened and how to fix it. Welcome to TheCodeForge. Before we dig into that production issue, let's design a proximity service. A proximity service takes a user's location and a radius, then returns all POIs within that circle. Without a spatial index, you'd scan every POI, that's ON, and doesn't scale. The key is to pre-filter with a Geohash or Quadtree. The naive approach computes haversine distance for every POI. At 10 million POIs and 1,000 queries per second, that's 10 billion distance calculations. Even with vectorized math, your CPU melts. The fix: use a spatial index to pre-filter to a small candidate set. This is the naive implementation. It loops over every POI, computes haversine, and checks the radius. For 10 million POIs, that's 500 milliseconds per query. At 1,000 QPS, you'd need 500 cores. Not feasible. Geohashing divides the world into a grid. Each cell gets a string ID, and nearby points share a common prefix. To find POIs near a user, compute the geohash of their location, then query all POIs with that prefix. This is a fast string prefix match on a B-tree index. Here's the geohash query. We compute the user's geohash at precision 6, which gives cells about 1.2 km wide. Then we query all 9 cells, the user's cell plus its 8 neighbors, to avoid boundary misses. This returns about 100 candidates from 10 million POIs in under 10 milliseconds. Geohashes have fixed grid size. If POI density varies, like downtown vs rural, you waste memory in sparse areas and lose precision in dense ones. Quadtrees adapt. They recursively subdivide a region into 4 quadrants until each leaf contains at most a threshold number of POIs. Queries traverse the tree, pruning branches outside the search radius. Here's a Quadtree implementation. The constructor takes a boundary and capacity. Insert adds a point, subdividing if the node is full. Query traverses the tree, collecting points within the search range. This returns about 50 candidates from 10 million POIs in under 5 milliseconds. This is the same issue we highlighted at the start. Here's exactly why that happened. The team stored full POI objects, addresses, metadata in the Quadtree. With 2 million POIs, each tilde 2 KB, the tree consumed 4 GB. During peak traffic, new inserts triggered rebalancing, which temporarily doubled memory usage, causing the OOM killer to strike. The fix was to store only IDs and coordinates in the Quadtree, and fetch full details from a cache or database on demand. They also switched to a disk-backed artree using SQLite's R*tree module, reducing memory footprint to 200 MB. Never store full objects in spatial indexes. A critical mistake is storing full POI objects in the Quadtree nodes. Each object can be 2 KB or more. With 2 million POIs, that's 4 GB of RAM, and during rebalancing, memory doubles, causing OOM kills. Store only IDs and coordinates, fetch details on demand. A common mistake is to query only the user's geohash cell, but a POI just outside the cell but still within the radius will be missed. Always query the 9-cell grid to cover boundary cases. Using a single thread pool for both reads and writes is dangerous. A bulk write operation can exhaust the pool, blocking all read queries and causing cascading timeouts. Always separate read and write thread pools. Here's the fix: separate thread pools for reads and writes. The read pool has more threads, and the write pool has a bounded queue to backpressure bulk imports. Also set a timeout on read tasks to handle slow queries gracefully. If your geohash cell size is larger than the search radius, you'll retrieve many false positives. If smaller, you may miss POIs. Always choose a precision where the cell diagonal is less than the radius, and query the 9-cell grid to avoid boundary misses. After retrieving candidates via Geohash or Quadtree, compute exact haversine distance to filter out points outside the radius. This ensures accuracy while keeping computation minimal. The article mentions separating read and write thread pools, but a common mistake is using a single thread pool for all operations. A bulk write can block all reads, causing timeouts. Always use dedicated pools with appropriate sizes and bounded queues. When debugging, first check if your geohash precision matches the radius and if you're querying neighbor cells. For quadtrees, verify that only IDs and coordinates are stored. Use profiling to check memory usage, and ensure read and write thread pools are separate. Let's run through some common interview questions. When choose geohash over quadtree, uniform density versus varying density. How handle concurrent inserts queries, read-write lock or lock-free tree. What happens at international dateline, longitude wrap, query wrap cells. And a few frequently asked questions. How implement proximity service, use spatial index like geohash. Geohash versus quadtree, fixed grid versus adaptive. How avoid boundary misses, query 9-cell grid. To recap, never compute haversign on all POIs, use a spatial index. Geohash is simple and works with any B-tree index, but always query neighbor cells. Quadtrees adapt to density, but store only IDs and coordinates, and always separate read and write thread pools to avoid cascading failures. Ready to go deeper? Up next, design Ticketmaster, then design a distributed job scheduler, then design Pastebin. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.